Good afternoon, good evening, good morning, everyone. It's my pleasure to introduce our speakers of today's webinar on PANGAEA, a global and inclusive benchmark for geospatial foundation models. So as you all know, geospatial foundation models have been really sort of revolutionized how we analyze a huge amount of Earth observation data for a variety of applications. Both our speakers have worked a lot on this model, so it's really my pleasure to introduce them. So Dr. Valerio Marsocci, he's a research fellow at the ESA's Phi Lab, especially working on the geospatial foundation models, focusing on benchmarking them for real-world applications. He received a PhD from Sapienza University of Rome, and he did his postdoc at CNAM in France and also KU Leuven in Belgium before he joined ESA recently. And Yuru is a PhD candidate at KTH, Royal Institute of Technology, and also in a joint PhD program at KU Leuven. He received his MSc from ETH in Switzerland, and he has also been working on the geospatial foundation model for Earth observation. So the floor is yours, both of you. So yeah, Valeria, please take the floor.
Yeah, hi everyone. Can you hear me better like this or
yes?
Nothing changed? Okay, perfect. So I will share my screen and you tell me now if you can see the presentation. Can you see the presentation?
Yes, now we can see your presentation. Yeah, go ahead.
Okay, perfect. Okay, so thanks everyone for being here, and thanks, of course, to Ifan for the invitation and to Geo Group. And we will structure the presentation in two parts. The first part will be an introduction on what's going on with benchmarking geospatial foundation model and why we made PANGAEA. And then Yuru will give you some more insights on how you can use PANGAEA in a fruitful way. For the question, please, I cannot see the chat in this moment, so please either just put your question in the chat and I will answer later, or you can just speak to the mic if it's something that I have to know in this moment. So, for example, if something is not going on in the presentation and so on. We can start, and I will ask every one of you to think about a real-world use case. So, for example, imagine that we have some Sentinel-1 and Sentinel-2 data, or more generally speaking, some optical data and some SAR data. We want, for example, to infer biomass height estimation, so the height of the vegetation, for example. Of course, we can use a model, so we can pick the best model out of it and to solve this task. But imagine that then, with the same model, we want also to solve another task that, for example, could be boundary delineation. And imagine that this happened with different sensors or with different modalities, with different kind of data, let's say. How to solve both of these tasks with the same model? Of course, you know, of course, the answer, because we're talking about the geospatial foundation model, but yeah, the answer is to use a geospatial foundation model. That is a model that is pre-trained on a wide set of data, diverse data, and very big amount of data to solve several tasks. But this is not enough to define a geospatial foundation model, because a geospatial foundation model must have different characteristics, and we end up in finding these five that basically are task agnosticism. So as I showed you in these two examples before, the same model should be able to solve different tasks independently from the task itself. So just a small decoder could be adapted, but most of the biggest part of the model, that generally is the encoder, should be the same, and the model should be pre-trained to solve both these tasks. Then these models should be spatial temporal aware, so they should work independently from the time and from the space in which we're using them. What does it mean? It means that the same model should be able to work perfectly in any part of our planet Earth. So both underrepresented and overrepresented countries, and this is a big issue that we will show you later, but also in different time steps. So imagine that we just have past data, then we want to like infer in the future what's going to happen, let's say. So that the same model should be able also, if we trained it on past data, to work on data that will just see when, of course, they arrive. Then we will talk also about sensor agnosticism. That means that this model, so a geospatial foundation model, should work, as you can see in this image that was taken from a recent paper published. It's a very nice paper about good foundation model, this DOFA, can work on a lot of different sensors without losing its capabilities. So, for example, with different sensors, we refer to, of course, different type of data. So you can see optical images that could be high resolution, but also optical images that are multispectral, but also other kind of both optical, like upper spectral, but also radar data and so on. But this is also true if we refer to same modality. So, for example, two multispectral sensors, but from different sensors themselves. So, for example, we can consider Leuven and Sentinel. So both of them are optical, but they retrieve different kind of information, also having different resolution, but just different sensor characteristics. And the same model should be able to work on both of these. This is very connected, of course, to multimodality in the sense that these are different modalities, but we can also think of other modalities that are not vision modalities. What do I mean? I mean that, for example, we can imagine having text. So this could be caption, or this could be any other kind of metadata, like coordinates, time steps, but also, again, length over classes and so on. And when we refer, of course, to multimodality, we refer also to these other kind of vision modalities that are not the sensors, but other products. So, for example, there are new models like TerraMind that are trained also on land use and land cover maps to help the model solve some specific task. And then, of course, we want, and this is very connected to the first task, but to the first point, but also to the other, we want this model to be adaptable in the sense that we don't want to retrain our model from scratch every time we have a new task or every time we have a new sensor, but just do some very, very small fine-tuning so that with a small amount of computation, we can have good results. This is also, of course, very connected to some issue about computational power that is very connected to carbon footprint issue, but also to democratize the access to geospatial data and artificial intelligence so that every lab, also small lab or any other kind of entity, could use these models without the need of, again, retraining or buying big data storage or computation plants and so on. Which is the main problem? The main problem is that at this point we understood, okay, we can use a geospatial foundation model because it can work on different downstream tasks, but at this moment there are tons of geospatial foundation models, and every of these models is claiming that they are working the best, not having a common framework, but just claiming it on their own datasets. And this, of course, totally makes sense because each of these models want to solve some specific downstream task as its specific protocol and was born for different reason. But then we need to understand which is the best among all of these so that we can guide the adoption of it, but also can guide some improvements. So how can we understand which is the best? That's easy, of course. We have to benchmark them and find out. But why benchmark is important? Yeah, I mentioned kind of fast. Of course, the first point is that we want to benchmark the performances to basically see which is the best. So to understand that, for example, one model is better than one other on the task we are interested into, and we will just adopt that one. But also, as I mentioned before, there are also other issues that are basically connected to the fairness and robustness. In fact, we observed that most of the pre-training data set and most of these models are trained on data that are coming from, let's say, some overrepresented countries. So there are more data on some areas with respect to other data. And as you can imagine, these data are coming mainly to the from Europe and from Western countries, just because to date these were had, let's say, more possibility to produce this kind of data. But this, of course, is bringing to some big fairness issue, making the underrepresented countries also less prone to have this application. For this, we are trying to understand which are the main drawbacks and which are the main drawbacks, of these models, and we would like also to take on this. And then, of course, these first 2 points are very connected to the third one, that is about guiding improvements, in the sense that if we find that there are some lacking fairness capabilities, in some robustness capabilities, or also in some just performance, we can observe that, I don't know, in agriculture something is not working or vice versa, we can totally guide the improvements of the new foundation model through the understanding of what's going on and what is not working. Maybe some of you are more familiar, just to make you better understand what we did, maybe some of you are more familiar with LLMs, so large language models, in which basically some models that some of us can use every day, like ChatGPT, DeepSeek, Gemini, or Claude, are benchmarked in a sort of arena in which they have a score, in which they are compared one to each other, so that we know, for example, as we can see in this image, that for text, so to produce text, Gemini 2.5 is better than all the others. But then on another end, if you're more interested in web development, then we should definitely use Claude Opus 4. So we want to do something similar. So to take the best geospatial foundation model, compare them, and be able to say, if you need this, then you should definitely check this out. And to do this, we made PANGAEA. So what is PANGAEA? PANGAEA is a framework that is putting together different sensors, different datasets from different sensors and different models. And in this way, we want to solve a diverse set of tasks under a standardized protocol, so that every model, we can really say if a model is working better than another one and under which condition this is true, so that for specific needs, we can decide to adopt one model with respect to another. This is just a general framework. If we want to focus more on the dataset, we can say that there are many datasets, and this could be easily expanded, as also Yuru will show you later. But basically, we have low resolution datasets that are, for example, like burn scars that are HLS, so harmonized Landsat and Sentinel. So, for example, this is an optical sensor with 30-meter resolution, 30 meter per pixel resolution as a special resolution. While for spectral resolution, we have 6 bands, for example, and this can solve some disaster mapping and more particularly some wildfire tasks. Then we have others like MADOS that is made of Sentinel-2 images and is about marine debris, so also for marine environment. So as you can see, we can also investigate a diverse set of datasets, a diverse set of sensors, because we don't have just a Landsat Sentinel, but we have also Gaufen, we have Planet, and so on. We have also Sentinel-1, so we have also radar, not just optical. We have different resolution, because as you know for sure, Gaufen is high resolution, while, as I mentioned, Landsat is lower. We have a diverse set of tasks, because we have segmentation, we have multi-instance segmentation, we have change detection, and then we have a diverse set of environments. So, as I mentioned, we have already disaster mapping, we have marine, but we have also agriculture, other kind of disaster mapping, and we have also land cover. And just to totally be clear, we have also other tasks like biomaster that are forest environment, and also we are planning to expand this towards other directions, the other dataset and so on. As I mentioned to you before, another thing that was relevant for us was to be sure that we could represent all the world, and we tried our best to collect the data that I showed you, because all of these are data that are already existing, and we want to represent, as I told you, a diverse set of our planet Earth. So we try to cover, given what is already existing, the world, and we could say that more or less we managed. Of course, as you can see, there are some specific countries that are underrepresented, like Canada or like Russia, but we can say that we cover most of the latitude and longitude, both in overrepresented and underrepresented countries. After that, we can focus on the models. So basically, we have this dataset, and as I told you, we selected some geospatial foundation model so that we could benchmark them on this dataset to see which are the best. Of course, the criteria, more than one, of course, to pick this model, where they should be open source, they should be relevant, and they should, of course, have some innovation in the methodology. So relevant in the sense both from how they were well received by the community and about of course, the innovation in the methodology. And as you can see, without getting too much into details, but we selected some data that have different pre-training strategy. So, for example, Chroma is on Sentinel-1, Sentinel-2, and this is very interesting for some stuff that we will see later. But also, Chroma was published in Eurips, so a very well-known conference, but also using some contrastive learning methods. Some other, like SADLAS, for example, were pre-trained in a supervised way that is kind of not so widespread in the Geospatial Foundation Model framework, because generally, most of them are pre-trained in a self-supervised fashion. And then we have also, for example, remote clip that is based on clip, so it's using some text. And so on, we have other kind of model, like also DOFA that I mentioned to you before. So we try to represent a diverse set, also in this case, of existing direction and models. After that, basically, we ended up with some results. Okay, now this is just a whole text of numbers, so I'm not expecting you to get something without my help. And so for this, I'm helping you, telling that in addition to the foundation model, we added also some baseline. And we added the unit and the VAT. So let's say the very widespread standards for any kind of task also in production. And in this case, we observed that there is a reason if unit is still one of the most adopted baseline also in production. And basically, we can see that it works, and it is ranked in the top two for 6 tasks out of 10, 11 maybe, 11. So just to show that it works very well if we know nothing about our pre-training model and about our downstream task. If we know nothing, then I will suggest you not to use a foundation model. So this can sound like a very bad news in the sense that, okay, so what are we doing with foundation model? Are they useless? And the answer then is no, they're not useless, but we really have to know something more than just, okay, I have a data set, I have a downstream task, and we have to solve this task. We need some more info about it. And on this, we try to focus on different aspects. So, for example, if we focus about resolution, to do this, we just grouped our results based on the sensor. And as you can see, of course, with each sensor come a resolution. So in the case of HLS, we're talking about 30 meter per pixel resolution. In the case of Sentinel, 10 meters. And then for this other, we vary from 1 to 3 meter per pixel. So very high resolution data set. We can see again that we can see some pattern. So for example, if we focus on Gaussian 2, in which we had the task that was a 5 billion pixel, that is a task of land cover, we can see that the data that can have best results for this are the ones that were pre-trained on high resolution images. So basically, to solve a high resolution task, it's better to use high resolution pre-trained models. And someone can say, okay, this sounds trivial, but I would say that it's not, because first, it's the first time that this is, extensively proved, and then second, at this moment, generally the state of the art were just suggesting to use the same model for all the downstream tasks. Well, in this case, this doesn't look like this. Then we will see that there are some innovation also about this, because we see that with new modality, maybe we can help also the guidance in this fine-grained information. But for the moment, we can say that if you have a very high resolution pre-trained model, so a model that was pre-trained on very high resolution images, then this can be way more beneficial for your high resolution downstream task. But also is the other way. So if we have a lot of multispectral bands, so if you have a lot of spectral information and less spatial information, so for example, Sentinel-1 and Sentinel-2 downstream tasks, and in this case, this is even more interesting because we had in our set of tasks more Sentinel dataset with respect to the Leuven-2, for example. We can really say that some models that were pre-trained on Sentinel-1 and Sentinel-2, in this case Chroma, are working the best. And if you want just to check how is working UNet, so the one that before was basically playing the best, you can see that basically UNet in this case is not the best at all, but it's not that bad. And this is true also if you check Leuven, but this is even true if you are checking others. Like for example, for Planet, this is a very good result, 62.1, but it's not the best because in this case, for example, for Planet, we have Scale MA that is working better. So in this case, we can say that UNet is very nice if you don't know your downstream task, but if you know something, at least about which sensor you're using, you have more chance to have better results if you take the most aligned pre-trained foundation model. And this is also confirmed by other experiments that show the same results, let's say, but in another way. So in this case, for example, we group the results with respect to the multispectral information. And again, in this case, you can see that some models that were having more information from a spectral point of view, like Chroma, that was pre-trained, as I told you, on Sentinel-1 and Sentinel-2, is working the best, let's say, because in average is, let's say, on par with UNet, but UNet is more fussy with the results. While some models that were just pre-trained on RGB bands, like Remote Clip or Scale MA, are really falling behind. On the other point of view, also you can see that where some models were pre-trained on RGB, like Scale MA, they're working the best. Something that some of you can note or can ask is, okay, but what about VIT? Why is working that bad? Yeah, basically what we observe is that VIT with respect to UNet is less shaped for geospatial data. And this is very interesting because most of these pre-trained models are based on a VIT. And so for this, we're also starting to experiment and to ask ourselves if VIT is the best model to have a geospatial foundation model, is the best backbone or not to develop a new geospatial foundation model. Because at the moment in the general computer vision is just the way to go. It's the easiest and is also the, we have most of the studies that can tell us which are the best hyperparameters, which are the best characteristics to train a VIT. But the question is kind of open because as you can see in this case, well, UNet that is fully convolutional is working way better than VIT in any kind of subgroups. And so this is also opening some question, and in the next steps, we're also trying to investigate more if the fully convolutional models are the best. If we go on, we can also see that we try to understand what happens if we have less labeled data. So basically, imagine that we have our downstream data that have, 2,000, 5,000 of labels, but what happens if we are reducing this number of labels? So our geospatial foundation models, so some models that were pre-trained on a vast amount of data, can they learn some information that are so useful in downstream tasks at the point that we have to rely on less data to have comparable performances? The answer is, again, yes and no. In which sense? In which sense that in some cases, like with Chroma, we can observe, for example, that for 10% of data, the results are better than UNet and also are the best in absolute. But on the other hand, we can also see that UNet is not working that bad. So also with less information, this unit can already learn some patterns that are then useful to solve the task, also when there are few labels. And this is so telling us some more insight, saying that maybe we should focus more on out of domain generalization. So if we pre-trained our model on a set of locations, set of sensors, and so on, this should be the model then should be able still to generalize to other location, either if we have a lot of data or very few data. And this is sometimes happening, but sometimes it's not happening. So again, as I showed you before, this can, for example, guide a lot the way in which we improve our model. Then if we want to move more on, not the result, but how PANGAEA was adopted and received by the community, I can show you, okay, we have a code base, then Yuru will show you better and will tell you also how you can contribute to this. We have kind of a lot of stars. We are almost to 200. They are more than 190 today. I just checked it out. But then also, other than that, we can also see that people can build very nice application based on it. So, for example, other models used it to benchmark their own model and to see, again, where they are lacking, where they should improve. So, for example, two of the latest are ENISA, that is going to be presented next week in CVPR, and it was also a highlight in CVPR. So we're very proud of it. And this was adopted without connecting with us. So just by themselves, also to show how easy it is to use this framework. But then also TerraMind, in which I work directly, that is this model that was developed by IBM and is a fill-out, so by us basically. That is, at this moment, we can say that is the first time that in average is outperforming also UNet. And this model was pre-trained mainly on open source data. Until to apply to be applied in some production some production level, at least to say, okay, through this I can say that UNet is the best, whatever, and I can use it. But we're also, of course, interested in pushing the boundaries more in general of AI4EO. And to this, we are also trying to investigate the embeddings, so how these models can, how they learn. So not how what they learn is useful, but also how they learn. So to understand what's already in these embeddings and what's not. And so we are adding, again, other tasks like classification, object detection, zero shot, KNN. And also we would like to engage more and more with the community, trying to launch some challenges also with the help of ESA, with their platform that is called AI4EO, in which we are planning to, again, to put some new tasks or new data set so that people can be stimulating developing new models to solve them. And yeah, so basically going towards the end, I can really say that it's very important to benchmark because this can tell us how to improve what's already there, how to use the already existing knowledge, but also how to push the boundaries to have better results. And these better results, once again, are not just from an absolute point of view, absolute performance point of view, but also in the sense of benchmarking the robustness and the fairness. So on the robustness, we're starting a new, let's say, branch of PANGAEA, trying to understand how this model can resist to corruption of the images and so on. And also, it's very important to underline how important is to have these projects open source so that all the community can use it, all the community, in which sense? In the sense of researchers, policymakers, any kind of stakeholders. And then, yeah, as I told you, we will have a lot of new steps, and I'm kind of excited about it. And I hope that also we can have some good collaboration about it. And finally, yeah, I want just to thank all the team that made this possible. And these were the authors of the paper that we produced, but then also now we are continuing collaborating with other people, with new people that are helping us in going towards different directions. So thanks a lot, and also thanks to you for your attention. And I will stop sharing the screen so I can listen to your question. And then, yeah, otherwise I will give the floor to Yuru. And thanks.
Right. Thank you so much, Valerio, for the excellent overview of geospatial foundation models in general and PANGAEA in particular. So very exciting, advancement, and also you plan to have the open platform challenges. This is great. Are there some questions for Valerio before we move ahead with Yuru's more hands-on training? So are there some questions? But maybe I don't see any questions. So maybe I have a quick question, Valerio. Let's say I work a lot with the wildfire monitoring. We want to detect burned areas of fire in near real time. Um, so which do you recommend? Do you think UNet is just a solution, or should I just use Chroma, the highest ranking accuracy? So which one do I use? What do you recommend?
Okay, on this, thanks for the question, because something that I didn't mention was that also we're planning in the next steps to try and have some thematic benchmarks. So, for example, we would like to add, if people is interested in forest, we will have a sort of section about forest benchmark. If people are interested in wildfires, wildfire benchmark, and so on. So, for sure, soon, I mean, in the future, we will tell you precisely, okay, you should definitely use this or that one. But for the moment, yeah, I would just say that it will more depend on the resolution. This is the first thing I would say. So depending on the data that you have, you can really say which model would be the best. If you have Sentinel data, I would say either Terramind or Chroma are the best at the moment.
Yeah, well, great. That's very good to hear that you're moving, more thematic focused benchmarking. Thanks a lot. I don't see any other, comments or questions. So maybe we wait till the end, and we will let Yuru present the practical part of this webinar. So Yuru, the floor is yours. Thanks, Valerio.
Try to share my screen.
We can barely hear you, almost not at all.
Okay, Yuru, increase your volume.
Okay, it's better now?
Slightly better. Keep it to the loudest on your computer.
Yeah, it takes some time to warm up my microphone. It's always.
Okay, now it works. Thank you. Yeah, please go ahead.
You share, sorry. Can you see my screen now? No?
Yes, very good. Yeah, thank you.
Okay, so thank you again for being here. So this session, I will talk about the design and structure of the PANGAEA benchmark that we developed. So it's gonna be a brief walkthrough. So we'll see how we, from the code perspective, how we address the challenges in evaluating geospatial foundation models in a consistent way. So first of all, let me direct you to our code repository as Valerio just showed before. So here is the link where you can find all the downloadable datasets and pre-trained models and all the code and configuration files that we used for the experiments. So this repository is actively maintained, and we also post updates and news. And we really welcome the contributions from the community, and we are always happy to see people building on top of PANGAEA. So basically, we'll go through like how PANGAEA is structured and how you can use it effectively in your own projects, and most importantly, how to integrate a new model or dataset into the framework. Let's start with the high-level architecture. So basically, PANGAEA is built around a modular design, and at the heart of this modularity is a configuration system powered by Hydra. So it's a configuration system that's developed by Facebook team. And this was a deliberate design because it enables maximum flexibility in experimentation. So here is an example configuration file, as you can see on the right side. This is an example configuration file that we used for training. So as you can see here, we can specify different models, different tasks, and different data sets. And you can easily swap out, like switch between different combinations of models or data sets or tasks so that you don't need to touch the core code. Then you can just run multiple experiments easily. So let's now walk through the how experiments are executed in PANGAEA. Well, you can find the complete workflow here. If you go to the repository, it's in the main script. It's called run.py file. So basically, the process begins with loading the configuration file using Hydra, and then we then initialize the encoders, which is your foundation model, and we load its pre-trained weights. And next, the decoder is set up based on the task that you've defined. And the dataset is loaded going through the pre-processing steps. And then if you are in the training mode, then the training loop begins. And finally, the evaluation is carried out on the test set. And all the results will be logged and saved. So if you're familiar with deep learning training process, this workflow is quite standard. Now let's take a closer look at the core components that make up PANGAEA. So basically, we have the engine component processor, and this manages the core training loops. So it does the core training loops, it computes the metrics, and it conducts data transformations and so on. And then we have encoders. These are the backbone of the system. So these are our selected foundation models, which are responsible for extracting meaningful features from geospatial imagery. We support a diverse set of models, as Valerio just mentioned. Yeah, and all of these are, if you go to the repository, you will see that it's under the encoder interface. And then we have datasets components. So we also, as you see before, we include a wide range of real-world datasets across different domains and sensor types and geographies, geographical regions also. And then we have decoder parts, which are responsible for task-specific outputs. So here, the decoder designs are tailored to the specific task that you've defined. Currently, PANGAEA supports a semantic segmentation task, change detection task, and the regression task. But we are in the process of integrating more tasks like classification and object detection. So today we'll zoom into the encoder parts and datasets parts. So that is the most two essential parts that if you want to integrate your own encoder model or your own custom datasets into PANGAEA to extend it. Okay, so let's take a closer look at the datasets part. Basically, the core principle for integrating new dataset is standardization. Basically, every dataset within PANGAEA is implemented as a Python class that's extend this base class called raw GeoFM dataset. So this base class provides a standardized interface for data access, ensuring the rest of the pipeline can interact with this data set that you defined. Then we have another class which is a wrapper on top of raw GeoFM dataset that it adds the pre-processing steps to transform your raw input data. And this wrapped GeoFM dataset is then the actual one that's integrated in the training pipeline to interact with other with encoders and decoders in the framework. So as I've just said, the standardization is very important to integrate your dataset into the framework. So basically, when you provide your own dataset, your returned atoms should follow such a structure. It should be a dictionary with images, which is your input data and target, and metadata as the keywords. And in your images, we currently support optical inputs and SAR inputs, and they should all adhere to such a tensor shape, which is the channel of your input and the temporal frames of the number of temporal frames, and then the h hat and the width of the tensors. And for the target, it should adhere to the shape of hat and width, and also for metadata. So basically, if you have only single temporal here, you still have to give a temporal number of frames of 1 to make sure that the dataset follows such a standardized structure to be integrated seamlessly to the framework. So essentially, in a practical way, to add a new dataset, that you have to do like essentially 2 steps. First of all, you probably already have your own Python class. You probably need to adapt it to extend the class from the raw GeoFM dataset that I just mentioned, and then provide a Hydra configuration file that specifies the accurate information of your dataset. So you can find all this detailed information in the repo. I will not go into the details here, but I can show an example. Like basically, these are 2 most important steps to integrate a new dataset. So on the left side, you see this is a definition of a new dataset class, and on the right side, you see you provide a corresponding configuration file that provides this the required information by PANGAEA. So basically, we ask you to include the image size, the multi-temporal information, the the number of classes in your dataset, and how many, and also one important aspect is to include what are the band information and the data statistics of these band informations in your dataset. So this, as I mentioned, these datasets, the raw dataset will go through some data preprocessors to do some preprocessing to transform your data. Here, we mainly support several datasets, several data preprocessors, including band management. Basically, it's very common to see a mismatch between the bands contained in your dataset and the bands of the foundation models pre-trained on. So to address this mismatch, we have several strategies, including band filter or band padding, to align the bands between the datasets and the foundation models. We also have normalization of the dataset and some spatial transformations and augmentations included in the PANGAEA framework. When you do the data preprocessing, you specify the order of preprocessing steps in the configuration file. These preprocessings are chained together to transform your data. Okay, so that's basically the brief overview of the datasets. And similarly for encoders, here you see, if you go to the REPL, to the encoders category, you see all of the encoders we currently support. By the name, you see that like remote clip, Prithvi, and we also support supervised baselines like UNet and the VIT. Yeah, so because we are evaluating their pre-trained weights, so we support automatic downloading of the pre-trained weights. That's an important function. And also you can find downloadable weights on the repo that I mentioned. And another important aspect that's worth mentioning is that we also support single and multi-temporal processing. Yeah, so basically, if you want to add a new encoder to add a new foundation model for fast benchmarking, similarly, you do two essential steps. The first one is create a new encoder class, and the second one is to provide a configuration file. Again, you can find these detailed steps, instruction steps in the repo. Here are the two examples. So here see like how you define a new model that this model should like inherit from the encoder class. That's where we specify all the required attributes and functions that you should include to be integrated into the framework. And again, on the provided configuration file example here, like this, you should provide detailed, accurate information about your models, including, like, for example, if it's a VIT, Vision Transformer model, what's the input size, what's the embedding dimensions, what's the patch size, and so on. Well, maybe I also mentioned the decoder part. Here, most of our decoders are primarily based on the Ubernet architecture, and we have specialized variants of Ubernet for different tasks. For segmentation task, we have single temporal segmentation Ubernet, we have multi-temporal segmentation Ubernet. For regression tasks, it's similar, and also for change detection task, we have CM's Ubernet variant for change detection. And as I mentioned, we have multi-temporal processing. Basically, we support two strategies to encode multiple temporals. This include a linear strategy and also a lightweight temporal attention encoder strategy. You find more in details in the repo. Here I'm mentioning that if you have a temporal data set, and this we also support that using a single temporal pre-trained foundation models to work on multi-temporal data sets for performance benchmarking. Yeah, so basically that's all you can find the more details in the repo again, and we really welcome the contributions from the community to include more data sets and more models. We are already contacted by several researcher groups that they are interested to include, to integrate their own data sets into the benchmark, and we are actively maintaining the repo. So yeah, that's any kind of contribution is welcome. And that's my part, basically. Yeah. Thank you again for your attention. Thank you.
Thank you very much, Yuru, for the detailed introduction. It's very, very helpful. I think I saw a couple of questions in the chat. I think the first question is to Valerio. I think from Johannes. I would like to extract urban footprint from modern multispectral EO data, from historical aerial imagery, and from scan and georeferenced historical maps. Is there a specific model could I try, or do I need to train a model from scratch?
Okay,
so Valerio?
Yeah,
Yes.
on this, again, my first suggestion is always to try to understand which is the characteristics of your data input data and see which are the, how they match to the pre-training dataset of foundation model that we selected. So, for example, again, if you have Sentinel data in input, I don't know, modern multispectral data could be this, I don't know. You could try TerraMind or Chroma, but then I would always try UNet, because UNet, it's very helpful for two reasons. Because the first one is that it's very, very fast, so you know very soon how it's going more or less, and you can also see if this makes sense or no to go on with trying other models. And then, of course, this is also because it's very fast and because it's a good baseline. And then something else that also was mentioned by Yuru is that we can both have different setup. So for the absolute performance, we can also fine-tune the encoder as well. So this can also boost more and more the performance, let's say. So also depending on what you are looking for. So if you're looking for something that is absolutely speaking the best performance, you should try also to fine-tune the encoder. But something that I would like to underline, then I finish my answer, is that, again, in this case, we are talking about geospatial foundation models, so some models that can work on a lot of tasks. If you already know that for your task, then your task is just very, very specific, and that just that one, maybe you have way more knowledge to shape a new model from scratch and so on. So it really depends on how many things do you need and how many effort you can put in it, how much effort you can put in it, both from a fine-tuning point of view and shaping the solution point of view. Thanks for the question.
Yeah, well, thank you, Valerio. So, Johannes, you have some more further follow-up?
No, that's fine. That helps a lot. Thank you very much.
Okay, thank you. Then we have a more specific question from Leonard. Do you want to say something, Leonard? Okay, I'll read it. How do you perform band padding? Simply adding 0 bands. Also, how do you normalize? With mean divided by standard deviation, or like the is often proposed by dividing by 10,000. So, Yuru or Valerio, who wants to answer?
Yeah, so basically for zero padding, if there are so if there are more bands in the data set and your models have all the only, for example, just require 6 bands, and in the data set there are 12 bands, and we'll do a 1-by-1 matching. And if there is a missing ones, we just do 0 padding for the model. And in terms of normalization, the current default setup that we used is the mean and standard deviation normalization. Yeah, but this can that's the one that's used by the results reported by PANGAEA, but I can see it also can depend on different data sets. Like for regression task, I think there's one regression task that's used mean and maximum normalization. Yeah.
Okay.
And then if I add something on this very shortly, is that in the paper we also show that for most of the tasks, there is not a great impact if you remove the normalization, for example. So in some case, also not using a rule could not impact the results that much.
Okay, thank you for the comment.